Okay. And in one of the examples that we talked about in the previous chapter, we found the slope of an arbitrary point on the equation 1 over a, okay? And we said that it was negative 1a squared, negative 1 over a squared, if you go back, okay? Now, so what we were doing, it was sort of like out of context. We don't really have an idea why we're doing any of this, but when you find the slope of a tangent line at a specific point, right? How did we do that? We did it using the formula, and then we said it's the limit as h approaches 0, right? So when we find the limit as h approaches 0, we have the slope of the tangent line at that point. And what we also have is the instantaneous rate of change at that point. Okay, so we had the function 1 over a. We found the slope of the tangent line, and it was negative 1 over a squared. That means at any point a equals 2, a equals 4, a equals 5. I could just plug it into negative 1 over a squared, and I can find the instantaneous rate of change right then and there. Okay? Now, this topic of finding instantaneous rate of change, this is pretty much the first half of everything calculus is. All right? So calculus can be pretty much divided into two parts. One is looking at rates of change. All right? And we call that part differential calculus. Okay? And what we did in chapter 2, which we had no idea that that's what we're doing, is we were looking at derivatives. Okay? We found a derivative. You had no idea, but when you were doing that, the limit as h approaches to 0 of f of a plus h minus f of a, blah, 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 you were looking for the derivative. So what is this word derivative? Well, this is important that you know that derivative is another word for slope of the tangent. Okay? And it's another word for rate of change. Okay, so if you're walking down the street and somebody says, hey, what's derivative? You say, it's rate of change. It's the slope of the tangent. Okay? That's what derivative is. Okay? All the time. Okay, now, a little bit of notation. Okay? So suppose y is f of x. All right? And you now want to figure out a way to symbolize f of x. You know how when we are looking for an inverse function, we have notation for inverse, and it's pretty much that, right? So to the power of minus 1, you see that, and you know it's inverse. Okay, well, derivative, right? The symbol for derivative is the prime. So you see here. So if you have f of x, the derivative of f of x, the symbol is f with the accent x, and we call it f prime of x. Okay? If you want to say you found the derivative of y, it's y prime. Another way to say it is dy dx. What does dy dx mean? What's delta? Change. Okay, dy dx is, d is also like delta, so it's basically, it's the change in the y over the change in the x. Remember, that's how you find slope. It's how much does the y change over how much does the x change. df dx is yet another way to do the whole thing. Okay, and now, so look, if you have df dx, if you write the f separately, right, it's the same thing, right? I just like physically separated them. And now what's f really? It's f of x. So you see how ddx of f of x is the same as all the other ones. Okay? So that's how you say it. It's ddx of f of x, or the derivative of f at x. Okay? So all of this means the slope of the tangent line at x, right? The derivative of f at x, the slope of the tangent line of f at x. That's what we said over there. All right. Okay. Definition of a derivative. Guess what? You knew it last year. You knew it in chapter 2. It's been with you all this time. All right? So the derivative of the function f with respect to the variable x is f prime. Okay, so f prime is the derivative. And the definition of the derivative is this. Okay, and this you've seen. You've seen the limit as h approaches 0 of f of x plus, exactly. This is what we were doing the last chapter. In the last chapter, we were saying that this is the instantaneous rate of change. In the last chapter, we were saying this is the rate of change at the point A. Now we're saying it's the derivative, because derivative is rate of change, derivative is slope, okay? Now, there are some functions, there are lots of functions to which you can find the derivative. There are some functions to which you cannot find the derivative at a certain point. If f prime of x exists, then the wording is f has a derivative. Another way to say it, f is differentiable at x. Remember when we were talking about continuity? I said we can talk about continuity over the life of the function, or we can talk about, is this function continuous at this point? Same thing here. We talk about, is this function differentiable at this point? Okay? And a function that is differentiable at every point of its domain, all right? If a function is differentiable at like over its entire lifetime, then we call it a differentiable function. So, you know, sometimes the problem will say, okay, suppose f is a differentiable function. That just means you can find the derivative at every single point. Okay? All right.
Wait, so that means there's like no like poles or like discontinuity?
No, it just means you can find the derivative everywhere. We're gonna talk about that, okay? That would be continuous, what you're saying. We're talking about differentiable. They're not the same thing. Yes?
I'm just confused. Like, I don't get what the derivative actually is. Like, we keep saying like f has derivative, but I don't know what it is.
Okay, do you know what this formula finds in the last chapter?
Yeah, for instantaneous
rate of change. Another word for that is derivative.
Okay.
This is just a different way of finding
if the instantaneous slope is the same as the regular slope, then it's all one differential function.
No, sometimes there are functions where you can't solve this for that point.
Right.
Okay? And those, we're going to do examples of everything, trust me. That's what this chapter is about, yeah.
If the instantaneous rate of change is the same thing as derivative, why didn't we just call it the derivative last chapter?
Because you also physically have to know that those two are the same. Okay, derivative is rate of change, but you also have to know where it comes from, and it comes from finding rates of change and bringing that secant line and making it. Okay, all right. So here's another vocabulary word for you: differentiate. Differentiate. This doesn't mean tell it apart from something else. Differentiate in calculus means find the derivative. Find the derivative of this. Okay. And now, this is the function we're given. Find the derivative means find the instantaneous rate of change at a point.
So we're doing the same thing we did last chapter.
Yes, we are. So, now though, we know what to call it. Now we're going to call it f prime of x. And it's going to be the limit as h approaches 0 of f of x plus h minus f of x all over h.
Why do you say f prime, like f prime of x instead of f of x?
Because what we're looking for is the derivative, right? And the derivative, the symbol for the derivative is f prime.
Do we need to also carry the f prime always?
No. So this is going to be f of x plus h is x plus h cubed minus x cubed all over h. Okay, now let's do x plus h cubed here on the margin. Okay, x plus h cubed is x plus h, x plus h, x plus h. Now, there is obviously a shortcut to do it. I don't want to spend too much time on that, but let's just multiply those two first. X squared plus 2xh plus h squared times x plus h. So now we distribute the x. So it's x cubed plus 2x squared h plus xh squared plus, now we distribute the h. So think back to plus h cubed. Think back to algebra 2. This is where you learn this. So basically you're multiplying a function by itself 3 times. Okay, so this is going to equal the limit as h approaches 0 of, okay, so let's take a look here. What we got in the green and the red. You have an x cubed, right? How many x square h's do you have? 1 and 2 and 1, you have 3. Those of you that were in my class last year and we did like binomial theorem, you know, that gave us the coefficients to expand this. So we could have done it that way. Plus, I have 3xh squares plus h cubed minus x cubed over h. So everything in the blue is what we did in the margin, and the green and the red. And then I just continued the function up top. Okay, so now what cancels here?
That's the third.
Correct. And can we save steps and get rid of an h here?
Yes.
1h, 1h. This becomes a 2, 1h. So finally, let me clean this up a bit. Limit 3x squared plus 3xh plus h squared. Okay? And now, what happens as h approaches 0?
We get rid of the limit and we put 0 in for...
Right? And so that will be 3x squared. So the derivative, f prime of x, is 3x squared. There we go. Congratulate yourselves. You just found your very first derivative.
Congratulations.
Okay?
How is this any different than what we were doing?
It's not.
It's the same.
That's the point. Is
Learning the name of it.
yes. We're now calling it something more
Mathematics.
yes, more elegant, more sophisticated. Yes. Okay. Use the definition to find the derivative of the given tangent at the indicated point. So now we're going to do it, but at the point a equals 2. So f prime, so now it's not f prime of x, it's f prime at a, okay? And what's a? 2. So it's f prime at 2.
So you use whatever variable for the prime, what they give you.
Right.
So since it was x in the first one, that's
Right.
x.
And now we actually have a number. So now it's going to be f of 2 plus h minus f of 2 over h. And it's all the stuff that we had done before. So this is the limit. H approaches 0. Okay, f of 2 plus h is 2 plus h squared plus 3 minus, what's f of 2?
2 squared plus 3.
Correct. Okay, so now this is 4 plus 2h, I'm sorry, 4h plus h squared plus 3 minus 7 all over h. So what is that? 4 plus 3, 7 minus 7 goes away. How cool. One of the h's will go away, yes?
Yes.
So we get limit as h approaches 0 of 4 plus h. And when h is 0?
4.
4. So we say, therefore, what does that mean?
The prime of 2 is 4.
No, what do those dots mean?
Ellipses. Right? Isn't that what it
Ellipses are these, dot, dot, dot.
Parabola.
The change is for?
Huh? It means therefore. Therefore, f prime of 2 is equal to 4.
Do we
Okay.
have to write therefore?
Huh?
Do we have to write therefore?
So do we need to only technically it's technically pure holes?
I can't draw
Holes. That's not a tiny hole. Do we need to draw the three of them?
So you don't need, it's,
Wait, do we have to do the dot thing or just?
I actually cannot
okay, you don't need to do the I'm just telling you guys some extra fun math stuff, okay? All right. So, okay, just a reminder, another way, sorry, another way to look at the exact same thing, to find the derivative of a, to find the derivative of f at the point A, okay? What you can do is you can pick 2 points. So now you want to find the derivative at the point x equals a. So here's what you do. Where is x equals a? Here. You go to x equals a, and now you have a and f of a, right? That's the point a and f of a. Yeah, you want to find the derivative of f at the point A. This blue function, the blue curve is f. You go to x equals a and you find what f of a is. That's that point. Okay? So, now you go to another point, a different point, anywhere else. Any random point here, x, and you look at f of x. Okay? So, this is f of a, this is f of x. All right, so let me repeat what I'm just saying. You need to find the derivative at the point A. So you go to A, you mark that point, and then you go to any random point, and now you have this secant line, right? Remember what we used to do in order to make the secant into a tangent? What should I do to those 2 points? Bring them closer to each other. If I bring them closer to each other, what value does x approach? A. So another way to look at it is, right, another way to look at it is the slope of this. Now what is the slope of this as is? F of x minus f of a, f of x minus f of a over x minus a. But as x approaches a, okay, this will be the same thing as saying as the limit of h approaches 0. Okay, so that's another way of saying the same exact thing.
But does A have to be 0? Or could it be
No, a is any point. A is any point. Okay, so now let's use that to do this. So let's use that definition now. Yeah.
If there's no specified number, should we say f of a, or should as x approaches a, or x approaches 0?
No, a. Okay. So now so let's use the definition then. F prime of 2 is equal to the limit as x approaches 2 of f of x minus f of 2 over x minus 2. All right? So this is the limit as x approaches 2 of f of x. What's f of x? Square root of x minus 1 minus f of 2, the square root of 2 minus 1.
Wait, is that 0 or 2?
Isn't as x approaches
2. Okay? All right.
Does it matter which way we do it?
So, well, here it says to do it this way, so we're following directions. Okay? So the limit of x equals, as x approaches 2 of, we have the square root of x minus 1 minus 1 over x minus 2. Okay, now, what happens when you plug 2 in here?
You'll get a 0.
You'll get a 0 in the denominator, and what will you get on top?
0.
A 0. You're going to get 0 over 0, which doesn't work. So now I need to do something with this in order to not get a 0. So remember, like, the things that we were doing is, like, you could factor, you could do common denominators, and so on. One thing that you could do is if you have a square root plus 1 or a square root minus 1, you could multiply by its conjugate. That means you can multiply this by the square root of x minus 1 plus 1, and you have to do the same thing here. Okay, so this is a trick that you do when you have a root minus 1 or a root plus 1. And what you do is you keep the outer ones the same, you just switch the minus to a plus and vice versa. All right? So now let's multiply these.
Does that only work if you have another number plus square root?
Yes. Okay, so now look at what we have here. I have a minus 1, a plus 1. What do I have when I have, what do you get when you get a minus b, a plus b? They don't cancel out, but
To foil them.
you foil them, but then there is a shortcut. If you have a minus b, a plus b,
It's minus b.
you get a squared minus b squared. Okay? That means you square the first one, you square the second one, you put a minus in the middle. So if you square the first one, root x minus 1, you get x minus 1. And then you square the 1 and you get a 1 and you put a minus in the middle. Yeah. On the bottom, let's not multiply, let's just leave it as is. Look at what's going to happen now.
And be able to cancel some of that. Oh, the ones are.
It's x minus 1. Okay, so what we got is the limit as x approaches 2, x minus 2 over x minus 2, x minus 1 plus 1. All right, what happens? X minus 2's cancel completely, so this is the limit as x approaches 2. What do we have in the numerator? 1 over...
Is this x for just 2?
It should be 0 or
2. It's a habit. So now this is going to be 1 over the square root of 2 minus 1 plus 1. So it's 1/2. Okay? All right. Okay. All right, so we're going to do the same thing, all right, using that definition. This is a different function. Now look, it says find d dx. That means derivative. Okay? And we're going to do the same as we did over there. Okay, so now it's at a equals negative 1. So this is going to be the limit as x approaches a, which is minus 1, f of x minus f of negative 1 over x, what? Plus 1, because it's minus 1. Yes.
Don't we have to put the f prime thing into it?
We do. Well, technically, in this case, it's asking you d dx. I mean, you can, or, you know, it's just the intermediate step. So, okay. So this is going to be the limit as x approaches negative 1 of f of x, which is 3x squared, minus, what's f of negative 1?
3 times negative 1 squared.
Right, which is 3. Can I just skip that step? Over x plus 1. Okay.
Wait, how'd you get minus 3? And you can factor.
It's f of minus 1. What's f of minus 1? When you plug minus 1 into 3x squared? Okay, so now this is equal to the limit as x approaches minus 1. Let's factor out a 3. So we get x minus 1, x plus 1 over x plus 1. Luckily, something cancels, so this is the limit as x approaches minus 1. 3x minus 1 So that's equal to 3 times negative 2, which is negative 6. All right? Now, let me give you another notation. Another way we can write this is d dx of 3x squared. Now, how are we going to do at the point x equals 1? Here's some cute little notation for you. Vertical line, at the point x equals minus 1 is equal to negative 6. So don't let all that scare you. This is all different notation that we're going to use, and it's foreign now, and I know you're going to ask me, do we have to put it in that notation? Eventually, it's not even going to be a question because you're just going to get so used to it, okay? So I'm showing it to you all little by little, exposing you to it. Yes?
So on the first half, or on A, you just wrote one half, you didn't. Why didn't you put all the information before?
Well, here, like the wording was f prime of 2, right? So we could have done f prime of 2.
Oh, so it wouldn't have been wrong if you did that.
No.
Okay.
Yeah.
So then it's interchangeable with the
Okay. What's another word for slope? What's another word for rate of change? Derivative. So now we have 3 words that mean the same. What are they? Slope, rate of change, derivative. Back in the day when you were 6th, 7th, 8th graders, you learned how to find slope of a line. How did you do that? Right? Or you would count up and okay? Now, here, okay, so derivative is slope, okay? If I have a function of f of x, so this is the original function, maybe it's f of x, we know that the derivative is just made of it's just the slope of the original. So if it's a function like this, you know, where it's just got linear functions, we can find manually what the derivative will look like because it's just the slope of all of these. Now, can I find the slope of this whole thing like that? No. How would I find the slope? Physics. You said the magic word, physics. Because if this is a graph of the displacement, then you can find the graph of the velocity.
Don't you just find the area?
Oh my god, go back. Here's how to test, but we all failed.
I'm barely passing the actual class.
Yeah, I mean, this class is a lot better than physics.
So the first, okay, what we're going to do is we're going to divide these into how many regions?
3.
One more.
4.
4 regions. 1, 2, 3, 4. The first region, no trying. We're not going to do the area. That's the other way. We're going to do the slope. The first region goes from 0 to 1. What is the slope of that part from 0 to 1?
1 over 4.
3 over 1.
3 over 1.
Negative slope would go down. This is increasing, so it's 3. So the slope is this. Now, here's what we do. Here's what we do. The second is going to continue where the first left off. At that point, I need to make this a function. So I can't have 2 closed circles. So I think ahead and I make one open in order to make the other one closed. So with each one, make the first one closed, the second one open.
But the first one's...
I'll tell you now. Let me do the second one. Here in region 2 goes from 1 to 3. What is the slope of that line? 0. So here the slope is going to be 0 from 1 to 3. Now, look at the green, look at x equals 1 on the derivative. If I'm going to close this. If the green circle was closed and the blue circle was closed, this would not be a function. I need to make it a function. So I, myself, make one open and one closed.
We choose which one we want.
Start with the, when you start this one as a closed circle, then there is only one way to go.
Okay.
Because it's closed, open, closed. Okay.
So you can only have one of each.
Yes, on each line.
Yeah.
Okay. The next one is in the region x equals 3 to 4, and what's the slope there?
-2.
-2. So it's -2. Okay. The last region,
But you better -1.
huh? Okay. Here we go. Just getting ahead of myself here. All right. The next one is from 4 to 5. And what's the slope there? 1. Okay?
We didn't do this, but like.
I have a question.
Yeah.
Why is that one open and that one, and the, you have to close it at the end?
I forgot.
No. Wait.
No, that one should be closed in the right?
Okay.
And you make it as like long as one.
Let's close this one.
Wait, so are both of them closed because it's the end?
Yeah. Okay. The thing is,
So start closed and closed.
yeah, start closed and closed. It doesn't matter here as long as as long as it passes the vertical line test. Okay? All right.
How did you choose at what height to put it?
The height is the slope.
The height is the slope. If m is 1, you put it at y equals 1. Okay.
Why is the first one closed?
The beginning and the end must be closed. In the middle, you can't have two closed on top of each other.
Oh.
Okay. Let's do one more. Okay. Shh. All right. Okay. Let's go back to differentiable, and let's talk about one-sided derivatives. Okay? So we say a function is differentiable. All right? I don't want to highlight all that. So a function is differentiable on a closed interval AB. This notation is very important in calculus. Like I said numerous times, most of the time we don't care about the entire function. Most of the time we're just looking at an interval from x equals 3 to 5, from x equals -1 to 0. So if we're looking at the interval a to b, what does it mean for a function to be differentiable? Well, it's differentiable if it has a derivative, but where? At every point on the interval. Okay, that's condition number 1. So if you're looking at the interval from x equals 0 to 5, then from 0 to 5, like the derivative must exist everywhere from 0 to 5. In addition to that, okay, the right-hand derivative of a must exist and the left-hand derivative of a must exist. That means not only should it have a derivative between 0 and 5, okay, at x, so if this is 0 and 5, you know, and if I'm looking here, that means at this point, the limit as I approach 0 from the minus side, it should exist. Okay? Now, let's do a couple of examples and see what we're talking about here. Okay. For example, take a look at this. X equals 0, right? Look at x equals 0. This is a square root function. Oh, by the way, I'm sorry, not square, absolute value. Is this function continuous? Yeah. Okay, now look at x equals 0. Is it continuous?
I thought so.
It is. It's continuous because look at x equals 0. What's the limit as you approach from the left?
0.
What's the limit as you approach from the right? What's f of 0? It's totally continuous. But now, look at x equals 0. Immediately to the right of 0, what's the slope? 1. Immediately to the left of 0, what's the slope? That means it's not differentiable at x equals 0 because the derivative from the left, the slope from the left and from the right are not the same. Yeah. Okay? So take a look at x equals 0. Immediately to the right of it, the slope is 1. Immediately to the left of it, the slope is minus 1.
Wait, so that's another condition?
Yeah, that's what this was here. Okay? Okay, so that means it is not differentiable at x equals 0. Okay.
So when would it be? When would they be?
Okay, here. This one is differentiable at x equals 0. Why? Because, take a look here. Okay, so this is x equals 0. Immediately to the right, okay, it's like this. But as you move down here, what's happening? The slope, so that's the slope there. And then if I go to another point, that's the slope. And then if I go to another point, that's the slope. So what happens is, for the absolute value, it's one slope and then immediately another slope. In this case, as you move here, the slope gradually changes, and it's not an abrupt change from one to the other. You see that? So because it's a round curve and not a corner, the slope doesn't change abruptly. It gradually changes to 0. So let's look at it another way. At the very bottom here, at the very bottom here, there is one instant where the slope is 0. It's horizontal tangent. Okay? Immediately before that, it's negative. Immediately after that, it's positive. But what happens is it changes gradually from positive slope to 0 to negative slope. So that's why it's differentiable. Now, how do you know? I'm going to tell you on the next page all of the different ways where it might fail. Okay?
So if it's abrupt change,
yeah,
then it's
right. If it's an abrupt change like a corner is an important word. If it's a corner, then it's not differentiable at that point. Okay, so here it says use a one-sided limit to show that the function does not have a derivative. Oh.
So they want us to function to
Oh, never mind. Huh?
So they want us to graph it?
No.
Oh, no.
Let's take a look at f of, so one-sided limit means we want to know f prime of 0 from the negative side, and we want to know f prime of 0 from the positive side. If those two are the same, then it has a derivative. If those two are not the same, then it does not have a derivative. Okay? So from the minus side, this is the limit as h approaches 0 minus of f of 0 plus h minus f of 0 over h. This is the limit as h approaches 0 from the negative side. Which function do I take, the top or the bottom? If I'm looking at 0 from the negative side, the top. Okay, so it's going to be 0 plus h squared minus 0 squared over h. And that's what? It's h squared over h. So one h cancels, and in the end, we get 0. Okay? Now let's look at the other one. The limit as h approaches 0 from the positive side, which function am I going to take? The bottom one. So this is going to be f of 0 plus h minus f of 0 over h. So this is the limit as h approaches 0 from the positive side. 2 times 0 minus, 2 times 0 plus h minus 2 times 0 all over h. This is equal to 2h over h, which is what? 2. All right? So, the limit, the derivative at 0 from the minus side is not equal to the derivative from the positive side. Therefore, no derivative at x equals 0. Let's take a look at y. What function do I have to the left of 0? It's a parabola, everybody's favorite function. What function do I have to the right of 0? It's a line. So take a look at what happens. You see how it abruptly changes from one to another? It is not a continual change in the slope. It's like a corner. Okay? All right? So this is all about derivatives. Now this homework... Whoa, I'm so sorry. 10 problems is due tomorrow. Okay?
Are they long problems?
Not all of them. I mean, it is what it is. We have to get through this chapter. It's a hefty chapter. We have to get through it. I know it's tough. It's the first time we're back for a full week. But,
Wait, this is really the first full week back?
I mean, since a while back, yeah.
Did you?
And then next week isn't even a full week. And then,
Next week isn't it?
well, there's PSAT. Oh.